Okay, now let's look at a new problem. In this problem, we have a ball attached to the end of a string, and the string is then rotated in a horizontal circle. So, since this ball and string system moves in a horizontal circle, immediately think about the possibility of circular motion. And then also at any instant in time, it is given that this string makes an angle of theta with the vertical. Okay, and our goal in this problem would be to find an expression for AC. Since we are not given any numerical values of any of the quantities here, we are looking basically to find a general expression for the centripetal acceleration for this kind of systems. It will work with any number, any numerical values, but we are looking for just a general expression. Okay. First of all, uh, because this will have a centripetal acceleration, since the ball is moving in a circle, right? Something is always making it accelerate at every point towards the center. Okay. At any point in this horizontal circle, um, the ball is being accelerated towards the center. Hence, there is centripetal acceleration. Next job is to draw a free body diagram. In this case, we have a free body diagram for the ball. What does it look like? We have the ball here. It has a mass m, so it will have a weight mg, and then it has a rope attached to it like that at any instant in time, making an angle of theta. And the rope, whenever it's attached to a mass, will exert a pulling tension force along its length on the mass attached to it, looking like that. And let's choose our axis so that acceleration direction is positive. If you're looking at this position in the picture, then you would see the acceleration is going like this, right? So acceleration, if it's the vertical, then acceleration is positive to the left. Hence, in this two-dimensional figure, I call plus x in the leftward direction and plus y, that is y in the y which is positive, upwards. Okay. What is the next job? Next job, we have to find components of this tension force, since it is not along any of the chosen axis we have chosen. Uh, any of the chosen axis, okay, that we have set up. It is at a weird angle, theta. That is our next job, to find components. Let's choose a different color for our components. What would the components look like? So if this is my chosen x and y axis, then tension is looking like this, right? And it is making an angle of theta with the vertical. So any vertical, it will make an angle theta. So in this case, the vertical is plus y, so it makes an angle theta. Since it's making an angle theta with the vertical, and we know how the x and y components would look like, it would be just parallel to the chosen axis, the y, or anti-parallel. Okay, so the y component would be looking like, if you go along the positive x-axis and look at the tension force, you would see that as you move along x, the y values are increasing, it's going up. So the y component would be going up. Let's call this green line Ty. This is the y component of the tension force. The x component is, if you go leftward more and more, you would see that along the t force, the x values are also increasing. So the component in the x direction must also be positive. So this is the x component. Now, as we know, this forms a right angle triangle. Therefore, we can just use trigonometry to find these components. And we know that the hypotenuse is nothing but the total force, or the total tension in this case. This is my hypotenuse. Hence, we can find Tx and Ty using usual trigonometry that we have so far used, and write down Tx as T sine theta and Ty as T cosine theta. So some terminology here, because maybe people may be confused about this. T sub x, this refers to the x component of the total tension. This T is the magnitude of the total tension. So this T is just the hypotenuse of the right angle triangle. Alright? Now that we have set up our forces along with our chosen axis, we can go ahead and write down Newton's second law. So we know that Newton's second law is a vector equation, hence we have to treat each x and y directions independently. In the x direction, what is Newton's second law for this problem? Summation of F in the x direction is equal to mass of the ball times A in the x direction. Let's look at what forces we have in the x direction. In the x direction, only force is the x component of tension. There are no other forces, right? So this would be Tx, and it is in the positive x direction that we have set to be positive. Hence we have plus Tx equal to, since there are no other forces, so nothing to sum to, equal to the mass m times Ax. What is Ax? This is a centripetal acceleration because it is traveling, it is making the ball accelerate always to a center of the circle. So we call this acceleration AC. We also calculated what Tx really is. Tx is T sine theta equal to MAC. What is AC? Well, AC, as we said, is the centripetal acceleration, and the magnitude of centripetal acceleration is written as AC is equal to V squared over R. Okay, so you can choose to use V squared over R in all problems that has centripetal motion. You can replace AC with V squared over R for centripetal motion. However, in this problem we are interested in finding what AC really is. We are interested to find the expression for AC. So we don't care about V here, so we just stick with what we know, what we want. Let's keep it AC. This is equation 1. In the y direction, what is our summation of forces? What is our Newton's second law? Summation of Fy is equal to m times A in the y direction. Well, what is the acceleration in the y direction? There is none, because this is a ball rotating in a horizontal circle. So there is no vertical motion. Hence, in this side, we have mass times acceleration in the y direction is 0. So this side is completely 0, meaning that the forces in the y direction are balanced, right? So what are the forces in the y direction? Ty and mg. So if this is Ty, it is balanced out by the weight of the ball. So Ty is in the positive direction minus mg in the negative direction equal to 0. Ty is nothing but T cosine theta, and that is equal to mg, right? Let's call this equation 2. So we want to find ultimately what AC, an expression for AC, a general expression for AC. So we want to get rid of any other unknowns. What is one major unknown in this equation so far? One major unknown in this equation is this total tension. We don't know what this total tension is, right? So our job is to keep AC in place and solve for AC, but however, we have to get rid of this tension. So we use equation 2 for that purpose. From 2, we can divide out T, okay, or separate out T. So keeping T on this side, if we divide both sides of the equation 2 by cosine theta, we get T equals mg over cosine theta. Let's call this equation 3. Now, wherever you see t, you're free to replace it by mg over cosine theta. So use 3 in equation 1 because there is a tension in it, a tension in this equation, T. So go ahead and do that. Then 1 becomes, using this equation 3, 1 becomes mg, in place of T, just write down mg over cosine theta multiplied by sine theta, right? We are just writing out equation 1, but everywhere where it is t, we are just replacing t by equation 3 here, equal to the mass times the centripetal acceleration. On both sides of the equation, we have the same mass, the mass of the ball. So the masses can be divided out. Alright, so what do we have left? We have left g sine theta over cosine theta equals AC. Sine theta over cosine theta, you can keep this expression as it is and say that this is your final expression. However, if we know a little bit of trigonometry, we know that sine over cosine is nothing but tangent theta, right? Therefore, finally we get an expression for centripetal acceleration for these kinds of systems. AC is equal to g, which is the acceleration due to gravity, commonly 9.8 near the surface of the earth, times tangent of theta. So this is what we set out to look for, and this is very general, and you can use this expression for any problem involving these kinds of circular motion, because it will satisfy the same problem for any theta. Theta can be anything, and for that specific theta we can find acceleration, and that the ball can have any mass. It doesn't matter. The centripetal acceleration for these kinds of systems doesn't depend on mass, as we can see from this equation right here. It depends on a constant g and depends on what angle it is forming with the vertical. So for any given angle, we are free to calculate what this acceleration is, regardless of the mass of the ball attached to the end of the string. Now let's look at a second part to that same question. Here, theta is given as 15 degrees. So this is the same problem of the ball attached to the end of a string and rotated in a horizontal circle. Theta is given as 15 degrees. The length of the string is given to us to be 0.8 meters. And we are asked to find how fast does this ball rotate in the horizontal circle. Alright? So what have we known from the previous part? We just calculated the centripetal acceleration for the system. For any system looking like this, a ball attached to the end of a string rotated in a horizontal circle will have centripetal acceleration of g times tangent of theta. Alright? Now theta is given to us, so g is a constant. So basically we can easily find what AC is. Also, we know from our basic study of circular motion that the magnitude of centripetal acceleration is given to us in terms of the speed, v squared over r, right? So anywhere you see AC, you can replace it with v squared over r. So let's do that and replace AC with v squared over r in our equation. So v squared over r is equal to g tan theta. Now we are looking for v, that's why we replaced AC with v squared over r. So let's solve for v squared first. Gives us v squared is equal to gr tangent theta. So we just cross multiplied r to this term. And if we solve for v, we just square root both sides and we end up with g square root of g r tangent theta. Now, as always, if you have a square root, this means there is a plus and minus sign here. However, speed is a magnitude and always positive. So we are just going to select the positive square root here. But what is this r? We know r to be the radius of the circle being traversed, right? In this case, the circle being traversed is formed by the ball as follows. So we have the ball with tension force along the rope. We know that the y component of tension looks like this, Ty, forms an angle theta, and we know the x component looks like this, and it is the only force in the x direction, and we know that there is a weight mg. Look at x forces in the forces in the x direction, Tx. This is the only force in the x direction. This means that this is an unbalanced force which causes this pendulum to always accelerate towards the center of the circle, alright, and hence keeps it moving in a horizontal circle. Therefore, r should be due to the length of this string at to which this ball is attached. Okay, the length of that string that we should worry about is as follows. This is the string of length L, and the string at any point forms an angle theta with the vertical, and so forms a right angle triangle. Okay, r would be the length of the string responsible for the circular motion. Which is the length of the string responsible for the circular motion? Well, this part of the length of the string, it's actually not a length of the string, it is just the distance covered when traveling around in a circle, which is always the same. This is the radius of that circle. How? This is the string, this is the ball, this is the vertical, and this is the horizontal, and this is the radius of the circle, which stays constant, but I'm a bad artist, so I'm drawing a very bad circle. But this radius is the one that is fixed when this pendulum or this ball goes around in the circle. So we are looking for this side of the right angle triangle. Okay, this is the right angle triangle we're talking about. So how do we do that? We know what theta is, we know what L is, we just want to find this distance, we'll call it r. So this is an opposite, that's an hypotenuse, so we use sine theta. So r is nothing but L sine theta. What is L? L is 0.8 and times sine of theta. What is theta? It is 15 degrees. So replace r with this here, so we get V is equal to G is 9.8 multiplied by R is 0.8 times sine 15 degrees times tangent of theta. Tangent of theta is, again, theta is 15 degrees, and square root the whole thing. We end up with the speed, that is how fast the ball is going in a circle, to be 0.54 meters per second. Right?